So we started section 1.2 last time, looking at finding limits graphically and numerically. We've done the graphically part, and we're moving today into the numerically part. So if you have, and I do hope that you do, your calculator with you today, you're going to want to use that next, okay? So again, numerically means with tables. So the question that we're on right now is question number 2, and it's going to say create a table of values for the function, and then use the result to estimate the limit. This is going to be a lot like what we did at the very end of section 1.1, but it's actually easier. It's easier because we don't have to do the calculating the slope part that was the more time-consuming part of that particular example. So I'm going to turn off the screen here and turn on the calculator screen, at least in theory. Well, let's see if we can get it to work today. Oh, look at that. Working for us. So nice. All right. So if you have a scientific calculator, you're welcome to use it. You can still do what I'm about to do, but there's really nice table features inside of the TI 83, 84 kind of versions of calculators that make this a lot easier. I'm going to go back through some of the prompts that we did last time in case you didn't get a chance to see that or you were struggling and you didn't want to talk to me about it in person. So we changed our table set. So table set's right there. So if I hit second table set, it should say ask on the first one and auto on the second one. It has nothing, doesn't matter at all what this table start is or what this delta table value is. Those don't matter, okay? Just say ask and it should say auto. Okay? So we're going to put in y equals the equation that we're given on this particular problem. So I have x squared minus 9 in the numerator. Now I have a TI 83, which means my operating system might look a little different than yours. Mine requires me to put parentheses around the numerator to make sure that it's really in the numerator, and the division looks like old-fashioned division, like calculator type. Yours might actually look like a fraction, and if it does, that's great. But this is the equation that we're given. Okay, is everybody able to get that entered in okay to their calculator? Okay, now I'm going to go into the table. So the table is over here underneath the graph button, right? And so in order to get this yellow table, I've got to hit second and then table. And I've got the buttons in, or the values in from the last time we did it together. So I'm just going to delete them out one at a time. And I'm going to put in the values that I need. So what values do I need? Well, it says that I'm wanting to find the limit as x approaches 3. So this table is set up like the other one we did. And I need values in my x columns that get really close to 3 from either side. So we do this the same way every time. We go slightly bigger than 3 and slightly smaller than 3. So slightly bigger than 3 looks like 3.1. But then it has to get closer to 3 as I go down my table. So I will go 3.01 and then 3.001. Slightly smaller than 3 is going to look like 2.9. And getting closer, 2.99, and closer still is 2.999. Okay, so before I go back to the calculator, do you understand where those values are coming from? Does that make sense? Okay. Let's say, for instance, you had something that was not a whole number. Like let's say that they wanted you to approximate pi over 4. Okay? You're supposed to find this limit at pi over 4. Okay, it's a trig function. They want you to do pi over 4. Well, grab your calculator for me real quick, just in the regular screen. What's pi over 4 approximately equal to? What is it? Does anybody know? 0.785. About? Okay, that's fine. That'll work. Okay. So if we were doing something like this, where it's not a whole number, what would we do? Well, we still want something slightly bigger and slightly smaller. And we have a little bit more flexibility, but we need to make sure we're really bigger and we're really smaller. So you might go with something a little bit smaller and just go 0.7. And something a little bit bigger and do 0.8. That would be bigger and smaller, right? But you have to make sure that you're getting closer to the 0.785. So when we do the 0.7, we might do something slightly smaller and go, okay, well, I could do 0.78. Okay, there's nothing special about my numbers. Mine could be different than yours and different than yours, and it'd be okay. They just need to be getting closer and still smaller. Are you guys with me on that? And you could be, okay, well, 0.78, well, maybe I go 0.784. Still smaller, but getting closer. And if I'm doing the 0.7 or the 0.8, it needs to be getting smaller now, closer. So we're like, okay, well, maybe 0.779. That's bigger than 0.785, but getting closer. Like, okay, well, maybe I do 0.786. It's bigger, but getting closer. So it's not that there's exactly one right value for these, but when we're working with whole numbers, like getting close to 3, naturally, these are going to probably match for most people. These down here, with my pi over 4 example, they may not. Okay, but they still need to follow the same basic principle, getting slightly bigger, getting slightly smaller to the value we care about. Does that make sense for everyone? Okay, so let's go back to our example itself. So we need to find the y values that go along with 3.1, 3.01, and so forth. So let's go back to our calculator, take a look. So we're going to do 3.1, 3.01, and 3.001, 2.9, 2.99, and 2.999. Okay, so I have the corresponding y values that I'm going to write into my table now. So I'm going to leave this screen right here where you can see my calculator, and I'm going to write it onto the iPad, and you guys can write it into your notes. So I have 6.1, 6.01, and 6.001. And then I have 5.9, 5.99, and 5.999. So this is what I wrote down from the screen. Do yours match? Yeah? Okay, so we go down each of the tables independently. And I know you might be looking at that and saying, but Dr. Hands, just like the last time, they're approaching the same value in both the tables. And they are in these two examples. That doesn't always happen. Okay? It doesn't always happen. So as I go down my first table, I'm getting close to 6. And I guess as I go down the second table of y values, I'm getting close to 6. So because they both get close to 6, we would say that this limit up here is equal to 6. It's probably worth noting that you can't plug 3 into this equation. Why not?
It's approaching 3.
It's approaching 3, but that's not exactly why.
The denominator.
It would make the denominator 0 on this one, right? Sometimes it feels like, well, I could just put the number in. Why am I making all these tables? Well, because sometimes you can't put the number in. And this is an example of one where you can't. If you put the number 3 into this expression that we were given, I'd get 0 in the denominator, and your calculator would give you an error, or you'd go, okay, I got a 0, what do I do with it? You can't actually evaluate this function at all. Now, you might remember, and we'll talk more about this in section 1.3, why that's happening for this one. This one actually has a hole in the graph. That's why we can get as close as we want, but there's actually not a value there. So there's a hole in this graph. Okay, so we'll look more at problems like this and learn more about that in section 1.3. All right, let's take a look at another one though. This one is actually, still has the same problem. I still can't put the number 3 in, right? So we're going to do the exact same thing. Our table is going to be set up the exact same way. I'm going to use all the same values. All right, 3.1, 3.01, and 3.001, 2.9, 2.99, and 2.999. Now, my table is actually still set up with those x values over here in the calculator. So all I need to do, if you notice the difference between problems 2 and 3, is that the numerator has addition in it instead of subtraction. So I can just edit the equation that's already in there. I don't have to type it all in again. That's not usually going to happen. I'm just going to type it in again, right? And usually the numbers aren't going to match from problem to problem either. But if I go back into my table, these are the values I get this time. So I can arrow over here, and I can see the display at the bottom. It really ends in 0.1. So this first value is 186.1. The next one is 1,806.01. And the third one is 18,006.001. Okay, so those are going into my list. If I go to the next one, I'm back at the 2.9, so I've got negative 174.1. I have negative 1,794.01. And then I've got negative 17,994.001. So a reminder about tables. We're going to write them down to 6 decimals of accuracy. Now, none of these needed 6. They all stopped at 1, 2, or 3 decimals, so it's fine that I didn't list out more. But if we move our cursor over on top of them, that's how we know. Right? We can see what the decimal expansion is down here at the bottom of our screen. If you're using a scientific calculator, you would just enter these in one at a time, and it would spit back out the value for you as well. Okay, you can do it that way. It's not a problem. All right, so as we go down our table now, what does it seem like is happening on this first list? Getting way bigger. Yeah, it's getting way bigger. So if that continues, what would we say that this is getting close to? Infinity, that's right. This is getting infinitely large. Now that's not a number, right? Infinity is this concept of getting way bigger, right? This concept of it never ending, that's a concept. But we would say that that's the value that we're getting close to. What happens on the right-hand side one though? Over here, my right side table.
Negative.
Yeah, this one's negative infinity. So if in fact we had the ability to talk about them being the same, like let's say they both said infinity, right? We could actually say that this limit is infinity from both sides. And we'll talk about that more in section, I think, 1.4. But right now they don't match, so it's sort of an irrelevant point. If they don't match, this is exactly what happened when we had this graph over here, where we had the jump in the graph, right? The limit from the right-hand side was 2, and the limit from the left-hand side was 1, and they didn't match. So since they don't match, the limit doesn't exist. Yeah. So the same thing's true if the values are infinity and negative infinity. If they don't match, the limit doesn't exist. Okay, so your web-assigned work, for the most part, is going to encompass the 2 concepts we've seen so far in this section. The graphics, right, the picture limits, and then the ones like this where we've got tables, okay? We're going to shift gears to what's going to be showing up on your written work now, because there is a written work associated with 1.4. So you'll have not only web-assigned, not 1.4, excuse me, 1.2. Not only web-assigned will be due for 1.2, but a written work will be due for 1.2 as well. So we're going to develop what's happening next. No, it's listed at the very bottom of the whole packet. Okay, so if you flip to the very last page, maybe that's what you were looking at. No, right here. It says web assigned homework, written homework, it lists some problem numbers. Do you guys see that? Okay, so we're still in the middle of notes. The homeworks are always going to be listed at the end. So I'd like to develop the idea of what's going on, of what we're doing, because it's going to feel less computational. We'll go with that. It's not going to feel computational at all. Computational is what you're associating with mathematics for the most part, right? Do you remember when you did geometry in high school? And there were these things called proofs, and it didn't feel like computation? Okay, well, this isn't a proof, but it's going to feel more like that, where it's not computational, okay? All right, so I want you to consider the function f of x equals 5x plus 2. And we're going to talk about finding the limit of 5x plus 2 as x approaches 3. So grab your calculator real quick. We've already got the approaching 3 business set up. We're just going to change it to, say, 5x plus 2. And look in the table. So as we go from, let me just draw in really quick little tables here. So if we have 3.1, 3.01, and 3.001, we have 2.9, 2.99, and 2.999. And our values are 17.5, 17.05, 17.005. The other one is 16.5, 16.95, and 16.995. Okay, as we go to the bottom of each one of these tables, what do we get? 17. Okay, so this limit right here is equal to 17. Okay, so that's what it's telling us. So this is the process. We can actually look at section 1.3. We haven't gotten there yet, and there's another way we can calculate this as well. But from section 1.2 that we're in, from a table, we can see our limit 17. Okay, so I want us to consider the graph next. So we have the graph. What is this an equation of?
A line.
It's a line. A line with slope 5 and y-intercept 2. So I'm sketching a graph. I don't need it drawn perfectly for us to make this argument. So I'm going to sketch it, and it's going to look something like this. That's not good. So at least make it look steep. Let's go with that. Okay. Steep graph, crossing the y-axis is the positive part. It's a reasonable sketch. Agreed? Okay. Our x value that we're concerned with is x equal to 3. So I'm going to put 3 right here. So if I were to sort of traipse up to the top of the graph, I'll dot it so that we can see where we're going. I'd be somewhere like that. The corresponding y value over here would be at about 17, like we've said. This is the picture that we're looking at. Okay, so the idea is that if we get really, really close to 17 on either side, so if we sort of get really, really close to this y value, that there's some corresponding interval around the x value that will force that to happen. Right? If I'm really, really close on the y value, I've got to be really, really close to that x value, and vice versa. Does that make sense? See, that's exactly what didn't happen on the graph from last time. If I got really, really close around here, there's no single y value that I could get really close to along the y-axis. On part of it, I'm really close to 1, and on part of it, I'm really close to 2. It failed to do that. But when the limit existed, say, for instance, here at 0, if I'm really, really close around the x-axis, I'll be really, really close around the y-axis. So when the limit exists, we have the ability to do that. When the limit doesn't exist, we don't have the ability to do this. Okay, so what we want to be able to do is to say, well, how close do I need to get? How close do I have to be to actually make that work? So let's say we want to make sure that the function value and the limit of the function as x approaches 3 are close to one another. That's what I just said in the other words, okay? I want to make them be close to each other. Perhaps we want them to differ by only 1 unit, right? We want to be within 1 unit of what we want. So we want to be within 1 unit of the y value. So this is my equation right here, 5x plus 2. This is the actual limit that I know it equals, 17. And we want to be within 1 unit around the y-axis. Okay, are you with me? So over here in my picture, we want this to go between 16 and 18. This orange is not a good color. Let me change it at least to red. So we want to go between 16 and 18. Okay, we want to be within 1 unit on either side. So if that's what we want to do, how close of an x value to 3 do I need to ensure that I'm at in order to make sure that I'm within 1 unit on either side? That's the question. How close do I need to be on the x-axis to make sure that that will work? So, So this is the question, is how do we fill in this blank? And here's how we can decide. We're actually going to do just a little bit of algebra. So we have that 5x what was it? Plus 2 minus 17 is less than 1. And we're going to simplify this expression. Okay, so first, the parentheses around here don't really matter because this is addition and subtraction, right? I mean, they're there, but we can combine the 17 and the 2. So this is the same as 5x minus 15. Okay, what can I factor out of 5x and 15? 5. So I'm going to factor that out, and I'm going to rewrite this then as x minus 3. This 5 here is positive, so I can pull it out of the absolute value as a 5, positive. If I had factored out a negative 5, I'd pull it out also as a 5, positive, right? So the absolute values definitely do apply with what we're doing here. This is 5 on the outside, and I still have x minus 3 inside the absolute value. And we'll divide by 5. And lo and behold, every single time we do this, we're going to end up with an absolute value of the piece that I want to consider. Look at that. That is not magic. That's math. This will always happen. That's our goal at the end of what we're doing here, is that we get the x minus 3 absolute value by itself. Now there's a trick when we don't have a linear equation. I'm going to show you one of them. But when it's linear, it always works out real smooth and easy. Okay? So the question is, I didn't write this down. This should say 1/5, not 1. The question of how close do I have to be is answered. I have to be within 1/5. Right? 1/5. So to be within 1 on the y-axis, I have to be within 1/5 on the x-axis. Why is that happening with the equation I'm given? The slope is 5. That's why it's happening. Right? The slope is 5. So that's why we're seeing this occur. Now, we sort of made up, I want to be within the value of 1 away, right? That was sort of just a random choice. It was done on purpose, but it's not particularly generic, right? It's not arbitrary. It was very specific. It was a value of 1. So what if instead of wanting to do this within a value of 1 around the number 17, I want to do it within an arbitrary amount around 17? Well, we're going to call that arbitrary amount epsilon. It's Greek letter epsilon. Okay. Look how it's written. It doesn't look like a capital E. It doesn't look like the little e that we use inside of logarithmic stuff, right? The stuff you've done back in Algebra 2 or a pre-calc or a college algebra class. It's not that e. That is the Greek letter epsilon. The problem, or the process by which we do this, though, is exactly the same. All right? We do the same math that we just did. We have 5x plus 2 minus 17. But instead of it saying less than 1, it says less than epsilon. And we simplify this to say 5x minus 15 is less than epsilon. And we recognize that I have the 5 that I can pull out of this. And then I can pull the 5 out of the absolute value. And I'm left with the x minus 3 inside the absolute value. And I can divide by 5. All the steps are identical. The epsilon's just in the place of the 1. And what we find at the end is much the same result that we found before. It's just that we find it with epsilon involved instead of a 1 involved. So this is epsilon over 5. It's arithmetic, algebra. It's stuff you've done before, but it looks a little funny. It doesn't really look quite the same, but the processes are the same. So we're going to do another one. Actually, before we get there, let me define what we're doing. All right, this is the piecewise definition of limit. I want you to star it, circle it, bold it, whatever you need to do. When we get to exam number 1, you're going to memorize this. Okay? You can do it? No, you can? You're going to memorize this. This says, let f be a function defined on an open interval containing c, but except possibly at c itself. Let L be a real number. The statement, the limit as x approaches c of f of x equals L, means that for each epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. So this piece, just going back to when we did, was the place where we kept starting. 5x plus 3 minus 17 is less than epsilon. The piece that came before it is actually the place where we were ending, right? The absolute value of x minus 3 is less than epsilon over 5. So we find the information that we're looking for backwards of the way that the theorem is written. Not the theorem, the definition is written. So I have 3 examples that we're going to take a look at. So you can see how we actually do these problems in full. Because I haven't done that yet. I just showed you where these epsilons and deltas are coming from and how they're related to one another. That's part of it, but that's definitely not in full. Okay, you ready to take a look? Let's do it. All right, we've got a line. This problem is going to feel a lot like the one we just did. So we want to find, or we're told actually, that the limit as x approaches -2 of 3x plus 2 is equal to -4. This says find the limit L. We're given the limit L here. If we weren't given the limit L, we'd have to use a table to find it, right? We could do that. You've done several of them today already. It's very nice that we're already given this. So here's how the problem will start. You start by taking the part that's inside the limit, and you put it inside of your absolute value. You can put it in parentheses, I will. If you want to leave it out, that's fine too. It's not going to hurt anything. And then you subtract the limit value, so we actually get minus a -4. So we want to make sure that we keep the negative from the actual limit value -4 down here, but we are subtracting that. If you do the wrong operation, you're going to end up getting a value that's not, you're going to be like, I don't get it. It didn't work out the way she said it would. So, do you have a question?
No, sorry. I was just, because I got confused because ours didn't print out the answer to the
Oh.
So that's why I was like.
Well, that's very interesting. Yours did not have it doesn't say -4. Okay. Write it in for me. I will go and I will change out my file in there. It's probably an old file. So, thanks for asking about that or mentioning it. You're always going to set that up to be less than epsilon. Okay, is everybody good? Okay, it's arithmetic inside, right? We're adding, we're multiplying, or dividing, these kinds of things. So I have 3x. I have +2 and -4. What's -4 going to be? Positive. So when I add them together, I get 6. So this is 3x plus 6. It is both positive. That is, the 3 at the beginning is positive specifically. So what value can I pull out of 3x and 6? 3. So I'm actually going to pull it out at the same time as I factor it out because I am pulling out a positive here. That leaves me with x, what's next? +2. Make sure you factor it out of both pieces. If you get, oh wait, one more step. Divide by 3. So the absolute value of x plus 2 says that it's less than epsilon over 3. This piece right here should match this piece down here. This says that x approaches -2. X approaching -2 means that I'm going to have an absolute value of x minus the limit that it's approaching, minus -2e plus 2. So when I get to the end and I get x plus 2, that is exactly what I needed it to say. That's the goal. This x epsilon over 3, remember, it tells you how close I have to be along the x value in order to achieve the y value approximation that I'm trying to get nearby y. Right? We found what x has to be in order to force the y value to be within that right range of values. This is half of the problem. Okay? If all you do is this part of it, you're getting half credit. Okay? This is the second half. The second half is a written proof. But the proofs follow the same format every single time. And they look like this. We know that the limit as x approaches -2 of 3x plus 2 is equal to -4 because for every epsilon greater than 0, okay, that's the epsilon we put in right here, epsilon greater than 0, there exists delta equal to, and it's what we ended up at the end, epsilon over 3. Such that and then we write it backwards. When this piece, the absolute value of x plus 2 is less than epsilon over 3, then, and we go back up to the beginning, the absolute value of 3x plus 2 minus -4 is less than epsilon. We're saying that when we get close enough around x, it's going to force it to be close enough around the y, because that's what 3x plus 2 is it's my y value. And it always follows that format. What's more is that if you know the definition right here, looks an awful lot like that proof we just wrote. It didn't have every single detail in there, but it has a lot of them in there. They go hand in hand. Okay, let's try another one. This one is squared. Does yours not have a limit like mine either? Just like this? It looks just like this? Awesome. Okay, so we're going to find it on this one. Okay, so we're going to do a table. Our table needs to be around the x value of 2. Let's get a solid line. So I've got 2.1, 2.01, 2.001, 1.9, 1.99, and 1.999. We're going to let our calculator do the hard part. X squared minus 3. These are the values I'm getting. If we go over on top of them, we'll be able to write them out. So I have 1.41, 1.0401, and then 1.004001 of 0.61. 0.9601 and 0.99601. Okay. What's the limit as I go down on the first table? 1. And the second table? Same thing, 1, right? So this limit is 1. Okay, so far so good? Okay, so we start this process the same way. We set up the absolute value, x squared minus 3, minus the limit, which is 1 in absolute value. This now says x squared minus 4. And all of this is less than epsilon. This looks different than the last ones. What did we do at this point on that last two problems we've done?
Factoring.
We factored, and we're going to factor here as well. Right, we are. We're going to factor, but it's not factoring out a constant like we did on the last two, right? That happened because we were dealing with lines, and this, my friends, is not a line.
Parabola.
It's parabola. It's quadratic, right? We're not going to be able to do that, but we can factor this. How does x squared minus 4 factor? Good. X minus 2, x plus 2. And one of those is the one we want. So don't everybody say it just yet. Think for a minute so everybody has a chance to think about it. Which of those two factors, don't say it, is the one we want? Okay, which one do you think it is? X plus 2 or x minus 2? It's x minus 2. Who said x minus 2 that I could hear it? Tanner, right? Tanner, how'd you know it was x minus 2?
Because the limit we're going towards is positive 2.
Correct. The limit we are going towards is positive 2, right up here. So this is the one that I want. So you might say, well, we'll just divide by x plus 2 to the other side, and we will not. That's not what we will do. It's very tempting. The reason that's not okay is because I need to have a concrete value, not a variable value. And if I divide by x plus 2, I've put a variable into the other side that I don't want there. So there's a trick. You ready to see the trick? All right. So what we do is we say, let's be really close to the 2. And we get to pick how close. So I'm going to go with, let me use some words here. Let's get close to 2. So let's say 1 to 3. That's pretty close to 2. If you don't like this and you want to make it even tighter, you can. But 1 to 3 will be fine. Okay? And what we're going to do is we're going to choose the maximum value on the interval from 1 to 3. So what's the biggest value if I'm looking between 1 and 3 on a number line? 3, right? 3 is bigger than 1. Nothing in before it's going to be any small. I mean, it's biggest, right? 3 is the biggest. The maximum value between 1 and 3 is 3. Everybody goes, I'll show you why we're going to do this in a second, I promise. But just bear with me so I can show you the process, okay? 3. We're going to pick 3. And what we're going to do then is we're going to be letting x equal this value. So the piece that I'm trying to get rid of, that's the x plus 2 piece, we're going to let that x value equal 3. Sort of seems like hand waving. Promise it won't in a minute. So I've still got my x minus 2. And now I have 3 plus 2. At the very least, I think we can all agree that's a number, where it was a variable before. That's also 5. So I have x minus 2. I have a 5 now, less than epsilon. So my x minus 2 is now less than epsilon over 5 if I divide it. So I got to the point where I have a constant on the other side. That is what I was hoping for, right? I wanted a constant on the other side. I've got that. Why did I want to choose 3 instead of choosing 1? Somebody was going to say what? It makes it smaller, right? If I choose 5, or choose 3 here, I get epsilon over 5. If I'd chosen the 1, I would have had 1 plus 2, that would be 3, and I'd have epsilon over 3. Epsilon over 3 is bigger than epsilon over 5. That's really why I'm choosing it. I want it to be a small interval. And 5, the precision will be more precise. Exactly. So I'm going for something that's going to make my interval smaller, and the bigger value, when I divide, will make my interval smaller. So my goal here, and it always looks this way. This is a pattern for the ones that you're going to do that have quadratics in them. You choose the bigger of the two values. You can always go 1 on either side. All that's just fine. We're going to get epsilon over 5. And then we're going to do that right up. Okay? And it mimics the same thing we did before. We know that the limit as x approaches 2 of, it's x cubed rather, x cubed minus 3 is equal to 1. Right? Back up to the beginning. We know this part is equal to 1.
X squared and x squared.
Oh, that's what you're looking at. Thank you, because I typoed. X squared. Let's go with x squared. X squared minus 3 is equal to 1 because For every epsilon greater than 0, there exists delta equal to epsilon over 5. Okay, remember, it always comes down from here. This is the first place where we're using information that we've created. The epsilon over 5 is. So the first part comes from the limit stuff that we did up here at the beginning, right? The next piece comes from what we created down here, such that when, and then we use the bottom piece, x minus 2 is less than epsilon over 3.
Epsilon over 5?
5. Thank you. Then the absolute value of x squared minus 3 minus 1 is less than epsilon. These aren't easy. They take getting used to. So don't rush through this written work assignment. This written work assignment is not what's going to be on your quiz, okay? These are called epsilon delta proofs. Epsilon delta proofs. Success Center can help you with this, okay? So go check the Success Center out and talk with them if this is causing you some struggles. Come see me if this is causing you some struggles. The written work will be only these epsilon delta proofs, and they will not be on your quiz. Okay? The quiz will be over the other material that we've covered in 1-2 plus 1-1. Yes, sir?
Where is the written work?
The written work's at the bottom of the page.
No, where do I find?
Oh, yeah, okay. So it's inside of WebAssign. So if you go inside of WebAssign where you would do your homework, there will be a link to an ebook where you can actually see all the different, you can see the whole book. But if you just go to like a textbook, yeah?
The textbook that we were supposed to get?
Yes, it's the same book, yeah. So there's loose leaf copies of it, there's hardbook copies of it, and then there's an ebook copy of it. So if you don't have a paper copy of it, it's inside of WebAssign, and you can take a look for these particular problems in section 1.2. That's where your quiz questions, if you're wanting to practice, are located as well. Okay, if you're having trouble finding it, ask somebody who's taken a math class. Well, that's not true. Ask somebody who's taken a calculus class here before. They can help you. Come see me in my office real quick, and I can show you where it is if you bring your computer with me. No problem. Any other questions? Yeah.
So you want it like on paper, or you want
It's
to?
on paper.
Okay.
The written work is on paper. So when you come to class on Wednesday, you're going to bring me a piece of paper, neatly written, right? Your name on it and all that. Okay, no frayed edges, please. And you're going to bring that and you're going to turn that in. At the same time that you turn that written work in, you're going to start a quiz right after we get started in class 2. Okay? So those are our 2 first things next time when we come back. And then we'll move into section 1-3 before we leave for chapel. Okay? All right.